So first, we have to know about some terminologies that we use in control systems, okay? So if we look at a control system, this is the schematic of a typical closed loop control system. So let's talk about it. The first thing we want to control the output of which is called a plant or a system or a procedure, right? So it could be anything, right? For example, let's say you want to control the temperature of a room, right? So this room itself with its walls is basically going to be your plant or the system you want to control the temperature of it. Or let's say it is a servo motor, right? And so the motor itself, the DC motor, is actually your system. You want to control the angle through which it has rotated. Or let's say it's a cruise control system in a car. So the system itself is car here, and you want to control the speed of the system. So it's anything you want to control the output of it. Now, so as I said, the variable from the system that you want to control is the output of the system, or one of the outputs of the system. You want to control that. Now, how would you do it? So now I'll tell you, there are two types of systems, and we're going to talk about it, closed loop and open loop. But in a typical closed loop system, what you do, you have a sensor to measure this output, right? So again, if it's the temperature of your room, so you need a thermocouple to measure the temperature of the room. If it is a servo motor and you want to control the angle, you have to have a sensor to measure the angle, and optocouplers is one of them, or any other device that basically converts the rotated angle to a voltage that you can measure. Or if it's basically the speed of the car, then you have to measure the speed of the car. Now, typically it is done by basically measuring the RPM of the tires and multiplying that by the radius of the tires. Or if it's sophisticated, you can use GPS to measure your speed. So you have to have a way to basically convert this output into something that you can compare against your desired output or reference variable. So typically it's a voltage. So you have a sensor, and most of the sensors, they have an inherent noise in them, okay? So you can barely ever have a sensor without any noise, so perfect number. Let's say another example is, I don't know, but probably you remember from your EGR 101 when you work with Lego robots and you wanted to control the distance of your robot to a specific wall or something, used an ultrasonic sensor. And if you remember, now that ultrasonic sensor is really a very, very cheap sensor, but if you remember that even if you kept it as a constant distance of, let's say, 5 inches, and then you looked at the reading of your sensor, right? So right, so let's say this is time and this is the distance that you were reading from that ultrasonic, and let's say you did not change the position of the robot, so you expect it to be staying at 5 inches, right? So this is what you ideally should measure, constant, But if you look at the reading, you see something like this. Okay, so it varies. If you record those numbers versus time, you see sometimes it shows 5.1, 4.9, 4.8, 5.25, and so on. So this is the inherent noise that exists in many, almost I would say all of the sensors, and it is typically inherent. And typically, the cheaper the sensor, the worse the noise is. And you have to have a way to reduce the effect of this noise in your control system. Many times applying a filter, we'll talk about it later, but applying like a passive or active low pass filter to reduce the high frequency noise. So there is a noise, and this noise will be added to the actual measurement, and then you get what? You get feedback. So feedback is what you measure from the output due to plus the sensor, the noise due to sensor. Okay, so that is what you send back to your controller. Now you want this output to be set at a specific input value or follow a specific time varying input. Okay, so let's say it's the temperature of the room. You want to set it at 70 degrees Fahrenheit, but now that you measure it with the thermocouple, it is 75, right? So you bring 70, you bring 75, and then subtract. Clearly, 70 positive, 75 negative, when you subtract the error, which is the difference between desired output or the reference variable inputs, that's the same thing, minus the actual output, right? So it's always desired minus what? Minus the actual. That difference here is going to be negative, so you send it to the controller. Now, controller in this case is, if it's a room, typically it's an on-off sensor, which controller, I'm sorry, which turns on or off the AC system, right? So if you need heat, it can provide heat. If you need basically reduction in heat, it can turn on the AC system and provide a little cooler air, right? And as I said, the plant here is the room itself with the wall, and it is affected also by the outside temperature. So heat induction and heat convection is really the major variable, or they are the major variables that affecting the performance of your controller. So this is a typical controller that you use in a thermal system. They are typically on and off, and because of that on and off strategy, they do not do a perfect job, because let's say here, if instead of distance it is really temperature T, so you want it at what? Let's say you want it at 70 degrees Fahrenheit, and the current temperature is at the moment is like 75. So when, let's say this is 75, and then here the controller turns on the AC unit, so to reduce the temperature, so it brings it down to what? It brings it down to 70 degrees. But since there is a delay, so as time goes, this temperature comes here down to 70 degrees, right? So here is when the AC goes on. Here is AC off. So it goes to 70, but the sensors are not transmitting their numbers, and the controller is not sending the control signal to the plant immediately, right? It takes, although very short time mostly, but there is a delay. So it takes for the thermocouple to change to sense the new temperature, send it to the controller. Controller calculates whether it should keep the AC on, or now turn it off because the temperature is good. So it takes a little bit time. And since in the meanwhile the AC is still on, what happens? Although you reach 70, but since the AC was on, what happens? You go a little further down. So you go to like 69, and now the controller has turned on what? AC off again. So what happens? The temperature tries to go, not tries, naturally, because there is heat coming from outside, so the outside temperature is more than the inside, so the temperature starts to rise. So it goes back again at 70, but what happens? Once you are at 70, the ideal temperature, then the AC is off. Now the thermocouple is catching up with the new temperature and measuring it and saying, okay, it is coming back to the normal, but before it can measure the new temperature, there is some delay, so this guy will pass what? The 70 before the thermocouple measures the new temperature, send it to the controller, and controller what? Turns the AC on back again. So it goes back on, but when you are probably at 71, and then it continues this kind of behavior. Okay, so you might not exactly 100% ever settle at 70. So you will go between two temperatures, let's say 71 and 69, or 72 and 68, or something. Doesn't need to be symmetric necessarily about the ideal, but there is this region, which we call it the dead zone, okay? And the on-off controller, they do not typically have the capability to exactly settle at this number and don't let it change. The more sophisticated controllers, you have the capability to exactly settle it at the angle you want. So if instead of that, that is a what? That is a servo motor, right? So this is a servo motor, angle versus time, right? So theta. When you tell it to rotate 45 degree, right? So you say, hey, go 45 degree. I want it to be settled at 45 degree angle. And right now, let's say it is not at 45 degree, it is at 0. So it starts increasing. The PID controller, we'll talk about it, that is on this servo, basically does what? It allows the rotation to happen. But if you want the same behavior, not once, but if the same behavior happens that happened for a thermocouple and a room temperature system, what would you see? If it goes to 46 degree, then goes to 43 or 44 and keeps oscillating, means your servo will never stop. It keeps going back and forth around the desired angle. But you never see that in real life, right? You always see that servo goes to some angle and then stops. It never goes and keeps oscillating about an angle, right? So although there is a behavior here, and we'll talk about it later, it's called underdamped behavior. Like a behavior can happen something like this. So there is some oscillation, but this oscillation, the PID controller, if it happens like that, it makes sure this oscillation damps out and you finally settle at what? The ideal temperature. Ideally, this kind of behavior should not happen. What you want is this exponentially goes and then what? Settles at the ideal number. Okay, so this red behavior, we call it overdamp, and we'll talk about it. This is an overdamp response, and the blue one, which there is oscillation but it damps away, it is called an underdamped behavior. So we prefer overdamp, or actually better than that, we call it critically damped. The other thing is this time it takes for the system to settle down at the desired number, or actually very close to that, which we call the settling time later, this number should not be big, otherwise your controller is slow. Okay, so there are too many things we have to discuss in this course, but I'm just trying to give you an overview. So the controller gets the error. Based on the error, it sends a signal. Now, as I said, the plant is not only affected by the control signal, there is another unwanted type of input to the system that is typically beyond your control, and it is not predictable most of the times, and that will change the output of the system. For example, if it's an airplane and what you want is to basically keep the roll angle or the pitch angle at 0, so you just want to cruise, right? You're at the high elevation, 33,000 feet, and now you're cruising up in the air. And when you're cruising, you want the angles of the airplane to be at 0 degrees, right? You don't want the airplane to basically bank or anything. You just want it to go straight on a line. So what can the disturbance be? Yes, it could be basically air pressure turbulence in the air, or it could be a side wind or a gust or anything that you don't know about it. You don't know when it happens, what is the behavior of that, what is the magnitude of that, and so on. And that comes and will tilt your airplane or change the angles. So one of the things that you want in your controller is it can react to those disturbances very fast, right? So if the wind comes and provides a little bit of pitch angle or roll and makes your airplane veer off from the actual track, this controller should act very fast, and using the ailerons or the flaps or rudder or any other control surface that you have in the airplane, it brings back the angle to the desired numbers and make sure you go back to the actual course, right? So these are all the components, and here I have provided the definitions for them. So control basically means forcing a system, a natural system, to behave in a way that you want. In other words, to produce the output that you want, which typically it does not do under normal conditions, right? Okay, and here I mentioned thermostat. The system or the plant is any combination of equipment or components act together to provide a specific objective, like a robotic sorting mechanism or anything. Disturbance, please pay attention. It's a signal that tends to adversely affect the value of the output. So disturbance is typically not there to help you. It's typically there to mess up with your work, okay, like the wind on an airplane. Or if the elevator is going down smoothly, then some person just jumps up and down in the elevator and mess up with the vertical position of the elevator. So it's not really there to help you, but this is an input to the system, okay? So disturbance is an input to the system, unpredictable, typically adversely affecting the output. Noise, on the other hand, is not predictable, similar to disturbance, but this is not an input to the system. This is due to sensor errors, due to sensor measurements, okay? So it comes typically from the technology that it measures the output variable. Feedback is the signal that is sent to the controller by measuring the output, which has also the inherent noise in it. An error is the difference between the desired output, which here we also call it what? Reference variable, and what? The actual output. So desired output, I can add for you here that it is the reference variable. That's the same thing. Okay, another example that I have provided here for you is one of the earlier controllers, which is called the Watts speed governor. So In the past, when you had an engine connected to a load and the engine is rotating, the shaft of the engine is rotating, so the goal was to control the RPM of the engine, okay? You want to keep it at a constant RPM. So why did you need a controller? Well, the problem is this. If the engine is rotating faster than what it should, right? Or if for any reason, for any disturbance, the engine, let's say you set it, you change the amount of fuel, this fuel that goes to the engine, and the amount of fuel that goes to the engine determines how much energy is produced in the engine, therefore determines the RPM of the engine. Let's say through this valve, the control valve, you set it, you fine tune it to what? So that the RPM of the engine is exactly what you want, right? So you are doing an open loop control system first. You're not measuring the RPM, you just say, well, I just open this valve and change it until the amount of fuel that is going into the engine is sufficient to give me the exact RPM that I want for the load, right? So you're doing basically a blind or open loop control, fine tuning basically. Now, if for any disturbance, anything to the system, this RPM goes up, okay? So there is any small variation in the fuel of the system, right? Or any variation in the load or anything that makes this RPM goes a little bit more than what you want. What do you think would happen if there is no control system? Well, so first of all, what was the mechanism for sucking the fuel into the engine? Because this valve just basically controls the flow, but there should be a change in potential energy, right, to make the fuel come from the fuel tank and be sucked into the engine combustion chamber. So where does that come from? Yes, that comes from the engine itself, right? So in engine, because of the rotation of the crankshaft and the down motion of the pistons after explosion, when they go down, basically there is a low pressure region that is created inside the cylinder, right? Because there was a mixture of air and fuel. Now it's exploded, created the pressure, and you move the piston, it moves the piston down, so that pressure is released and is converted into kinetic energy for the crankshaft. So the piston goes down and then the exhaust valve opens, so the rest of the mixture gets out of the cylinder. The piston is down, and what happens? Yeah, you have a relative vacuum created inside the cylinder. Now you close the exhaust valve and open the inlet valves. Now what happens? Yes, since you have a very low region or a relative vacuum inside the cylinder, that causes the fuel to flow into the engine. Yes? Good. So that's the mechanism for bringing in the fuel, or at least that's what it used to be in basically older engines, the ones that did not have an injector, the one that had a carburetor. And by the way, these are the 4 stages of an internal combustion engine, 4-stroke cycle, we call it. So basically, as I said, this is the intake stage where the fuel comes in, and then you have the compression, and then the explosion or power, and then the exhaust. So it's during this stage where the inlet valves are open, the exhaust valves are closed, the piston is down, so there is a low pressure region created here which sucks in the air and fuel. So in the old engines with carburetors, there still might be some of them around, but now these days mostly they are using injectors. So just the air comes in and the fuel is injected by injector. So the mechanism for controlling the amount of fuel coming in is separated from the air inlet, but in the past that they both came together, and the amount of inlet fuel and air mixture was determined by the amount of pressure, low pressure in the engine, there was a problem. Again, what is the problem? If for any reason, for any disturbance, again, it can be any change in the load or any change in the location of the valve or the viscosity of the lubricant in the system or anything like that, the RPM goes up, let's say a little bit. What happens? Now your crankshaft is rotating faster, and when it rotates faster, what happens? So since this guy moves down faster, the vacuum that you create here is going to be a little bigger. The change in pressure is going to be bigger. So you have a bigger change in pressure of the combustion chamber, right? So it's going to be lower than it used to be. What does it mean? Means the amount of suction on the fuel will be bigger, right? So you have a bigger vacuum, it sucks in more fuel, and when more fuel comes in, what happens? Yes, the explosion will be more powerful. The energy that is released and the amount of push on the piston and the amount of RPM accordingly on the crankshaft will be even faster. So what happens? Yes, the crankshaft will rotate faster, and the faster it rotates, again, the bigger the vacuum is going to be, the more fuel comes in, and you see that's this vicious cycle, right? That the system is just boosting itself more and more and more and more until what? Yes, the system cannot hold more RPM and your engine would fail. Correct? It cannot just keep increasing its RPM. After so much of RPM, your mechanical parts would fail and you're gonna have a huge bang noise and the engine would stop. So what Mr. Watts did was he had this governor mechanism to make sure that the system does not increase its speed continuously until it fails. So what did he do? What he did was he used a couple of bevel gears and basically transferred the RPM of the engine to a governor mechanism. So the RPM is directly transferred to the shaft of this rotating mechanism here. Now, this rotating mechanism has two weights, okay? And these weights are pinned at these 2 points and free to rotate. So since they are acting like pendulum, the faster that you rotate this shaft, or the faster the engine rotates, the faster this object spins about itself. And when this object rotates faster about itself, the angle of these two pendulum, or pendula if you want to call it, will be bigger and bigger, so they spread out, okay? So initially, if this angle is like 30 degrees with respect to vertical, the faster you rotate it due to the centripetal, or you might call it centrifugal force, you would have these two pendulums more extended, right? And then what happens? Okay, what do you think? When these guys extend out, they need more force to rotate them at a larger distance, right? Because the distance of these two weights from the axis of rotation gets bigger, so the moment of inertia gets bigger, right? So you know from your statics or dynamics course that if you have an axis, and if you have a mass, m, and the distance of mass to the axis is called d, so the moment of inertia, j, of the mass with respect to axis is calculated by what? M times d squared if it's a point mass, yes? So the bigger D, the bigger J. And you know, torque that is applied to an axis is equal to what? J times theta double dot, or alpha, right? So if D goes up, what does it mean? It means J goes up, right? T went up because you inserted more fuel into the system, right? It's a vicious cycle. The torque is going up because you are burning more and more fuel. So the T is going up. If you keep J constant, right? If you keep this moment of inertia constant and T goes up, what does it mean? It means alpha goes up, and alpha is the angular acceleration of the shaft. The bigger it is, it means omega will keep increasing more and more, right? The RPM. But if through this mechanism, what you do is when RPM goes up, you make D go up. When D goes up, J goes up. So T goes up, J goes up. What happens to alpha? You try to keep alpha constant. Okay, so this alpha does not change. If you can make sure that J and T go up the same amount. So T gets twice big compared to the last time. J also gets twice as big. Alpha does not change. And when alpha does not change means omega stays constant. So your RPM does not change. So you stop that vicious cycle, right? So the mechanism is basically increasing the moment of inertia of this object, which is a weight, and two pendulum attached to it, increasing the moment of inertia of that due to the centrifugal force. We can talk about it later when we get to the modeling of mechanical systems, and that is resulted from RPM. So you see, this is a feedback system. You are getting a feedback through these gears, and then say, well, that's more than what I need, so I extend this pendula such that J goes up and alpha does not change and omega does not. Alpha stays the same and omega, rate of change of omega stays the same. Okay? And then basically it wasn't exactly like that. This object was connected to a spring that was preloaded, and that shaft was connected to the hydraulic valve, and the hydraulic valve was controlling the position of the inlet valve. So what happens really is, as these two guys extend, then not only this RPM changes, the vertical position of this object, which can freely slide up and down here, this point, this plate here, this black plate, the vertical position of that can change accordingly. Because if you see, this vertical plate is connected to the pendula. So when pendula extend, this black plate goes up. And when that black plate goes up, it is connected to this shaft, so this shaft goes up. And so the amount of position for the inlet is controlled through this 3-2-way hydraulic valve. Okay? So it's a little more complicated. But again, the mechanism is you control the position of the inlet fuel valve by getting a feedback from RPM. RPM goes up, this mechanism will what? Shuts the fuel valve a little bit, right? And if RPM drops, this mechanism will open up the fuel valve a little bit to bring back the RPM. So that's what happens through this entire mechanism. Again, here, if you say the input to the system, actual input is fuel, and that's what you can control. The output that you want to control is what? RPM. The controller is this governor. It is acting based on the centrifugal force and the position of this black plate that controls by itself the position of this spool of the 3 two-way hydraulic valve, and that controls the position of the fuel inlet valve. So it's quite complicated and not super complicated. The motor controllers are way more complicated, but you can see the genius of this person in stopping that vicious cycle of the engine and making sure that it can never boost its RPM to go up further, or drops its RPM further until it stops. It can keep the RPM at the desired level. And how would you change that desired level? Actually, the desired level was controlled by the tension in this spring. Okay, so depending on how much pre-tension you create in this spring, you could basically change the position of these valves and so the RPM of the engine. So it is an interesting mechanism by itself, but let's go to the next slide. So now there are two types of controls, a closed loop and an open loop. The closed loop is what we have seen. You get a feedback from the output and measure it against what you really want, and based on the difference, we call it error, you decide what to do. In open loop control systems, there is no feedback. It's just direct going from input to output. So this portion, this bottom portion, does not exist. So how would you control really? It's just fine tuning. Okay. So like what? One example is a laundry machine. So in a laundry machine, what would you do? What is the desired output? Well, cleanliness of the clothes, right? You want the clothes to be clean and probably smell nice and so on. Well, do you have a sensor in your laundry machine that determines, hey, now the clothes looks nice to me. I don't see any spots or any dirt or stain or anything. And yeah, I can smell, they smell really nice. So it's time to turn the machine off. Do you have a sensor like that? Of course not. So how would you know? Right? How would you know what time of the laundry machine to use, how much liquid you would use, and so on? You just need to fine tune it. So there is no control really much, and you are fine tuning it and finding based on your experience at what amount of liquid and how much of time and what temperature of the water it will do the job, right? So you fine tune it and make sure the system works. Or gas oven, right? When you're baking something, do you exactly have a mechanism that measures the readiness of the food? So it says, okay, now I guess the food is ready, or we are barbecuing something. It says, well, I think now the steak is ready. It's well done, or medium rare, or something. And I guess now it's time to turn the grill off. Do you have a sensor like that? Of course not. So how would you know how much you should leave it on the grill and how much of basically heat is enough? Well, you have to fine tune it and do it several times based on trial and error to find it. So it's not really a control. It is because you are changing the amount of inputs to the system, but you're doing it in a blindfold manner, right? You just do trial and error. But car control for cruise, that's not the same, right? You do not basically fine-tune the position of the accelerator and the brake to determine the desired speed of the car. It will do it by itself. Or thermostat, you don't come and stay right next to your temperature control unit and turn the furnace off or on, or AC on and off until you get to the desired temperature. The system turns on and off by itself. So that is a closed loop, because those systems have a way to measure the temperature of your room. They have a way to measure the speed of your car, comparing it against what you want, and then determine how much input should go into the system. So we have open loop and closed loop. And what's advantage or disadvantage of each one? So open loops are, as you can imagine, they are very sensitive. Okay, and they are not robust, which means their performance does not stay consistent. Why? Because let's say going back to the grilling example, you're baking something, you're cooking something, grilling something, something like that. And one time you have a thicker meat that you're grilling, sometimes you have a thinner one. So you have to pay attention. The system does not have anything. So if some parameter of the system changes, the system has no smartness, have no way to measure. Therefore, any change in parameter of the system will completely mess up the system, right? If you were in charge of keeping the temperature of your room at a desired number, what can be a change in parameter of the system that if at day one you exactly know, okay, now at 1 p.m. I turn the furnace off, at 2 p.m. I turn AC on, at 9 p.m. I turn the furnace back on, and so on. So you figured it out today exactly when to turn on and off the two mechanisms. Now tomorrow, what can change that completely mess up your calculations? Well, yes, the outside temperature. So today you set it everything for the outside temperature of 75, but tomorrow there is a heat wave like right now, and the temperatures are in hundreds, so you have to completely basically change what you have done. So open loop control systems are very sensitive and they are not robust against change in parameters, against external disturbances, and they are not really as stable as a closed loop. And stable means basically they can keep their performance. They are not underreacting or overreacting and lose the control, right? We'll talk about stability more and more mathematical definition of stability. But basically, could you keep up with the output and keep your performance, or you would lose the battle and overreact or underreact until it is completely out of control. So that's stability, and we talk about it more. So if closed loop systems provide all of this robustness, stability, and everything, right? Then what's the point of having an open loop at all? Why should we have an open loop? Because it's not real control. So two reasons. One is they are not as expensive because they do not have sensors, much of a controller, and so on. They have a lot less equipment, so they are cheaper. Okay, they need less power to operate, less resources, of course. Okay, so that's the only advantage they have. So there are some applications that you do not have much of disturbance and much of change in parameters, so you can rely on a cheap fine-tuned controller to get your job done. And one other reason that I have not mentioned here is sometimes you cannot really measure that desired outputs or the actual outputs, right? Or it's really hard. In a laundry machine, how would you really want to measure the cleanliness of the clothes? Right? You have to stop the machine, basically, and the clothes that are entangled together, you have to kind of move them around, lay them flat, and then you have to have a sophisticated image processing system that determines whether there is any stain or dirt or anything left or it's good to go. Right? It's not that easy. Or in a grill oven, again, the same thing. You need a sophisticated image processing, some way to cut the steak and see in between whether it's rare or well done or something like that. Okay, so these systems are not cheap and not easy to create and maintain. Therefore, sometimes we have to do that fine-tuning. It's cheaper, and it is the only way that you can do it. So that's the difference between open loop and closed loop. And again, I mentioned examples of each. And so this is a very basic thing that we had. By the way, one last thing, noise is typically not something that you can completely eliminate, okay? So it's generally signal resulted from technology. Let me add something for you. Noise is inherent to the sensor and is not possible to physically eliminate. So we cannot completely eliminate the sensor noise. The sensor will always have noise. But do we send that noise directly to our controller? No. In controller, we have some ways to reduce the effect of that noise. As I said, filters, passive filters or active filters, low pass filters. So we try to mitigate the effect of them. But can we separate this noise from the sensor in the first place and send a clean signal directly here? No. Each sensor has inherently some noise in it. So we cannot just remove them and make them not exist, but we can mitigate their effect later when we go and send those feedback signals here into the control, or we can put them right after sensor. So a portion of the controller can be right here. Before you compare it against the inputs, you can do some filtering here, okay? So just wanted to tell you about one more point about noise. Okay, so I guess I have covered this topic, and I will see you in the next lecture. Thank you.